I am so glad you're here. Let's jump right into covering all the reactions covered in Organic Chemistry 2. One of the first topics typically covered is dienes. Specifically, we need to know how to make them and then how they react when presented with electrophiles. In order to generate conjugated dienes, we need to begin by doing an elimination reaction. In certain circumstances, we have a single halide or we have a dihalide species. In both of these examples, you can do an elimination reaction to form your conjugated diene, and in the presence of potassium tert-butoxide, both of these reagents would produce a conjugated diene. When reacting a conjugated diene with HBr, you typically always produce a 1,2 adduct of the addition of the bromine and the hydrogen. So this would be the 1,2 adduct because the hydrogen and the bromine go at positions 1 and 2 on the carbon chain. And in addition to that, you also generally produce a 1,4 adduct. So in this case, you would produce a hydrogen at this location at the 1 position and a bromine at the 4. We have called these previously the kinetic product and the thermodynamic product. So the thermodynamic product is going to be your 1,4 addition and your kinetic product is going to be your 1,2 addition. In addition, we can add bromine gas or Br2 to a conjugated diene and we would get the same 1,2 adducts and 1,4 adducts. Specifically, this is going to generate a bromine at the 1 position and the 2 position. This would be the kinetic product, or the 1,2 addition, or the 1,4 product, which is going to be the thermodynamic product. And importantly, depending on the conditions of the reaction, that is going to generate the major product as being one or the other. So for example, for kinetic products to be formed, you generally want low temperatures, like at 0 degrees Celsius, and a very short reaction time. However, for something like the thermodynamic product, you generally want higher temperatures and a longer reaction time. Pause the video, try these problems independently, then resume the video to check your answers. In all Diels-Alder reactions, you always start with a conjugated diene reacting with what is called a dienophile. And these electrons in the pi system are delocalized such that they can form a cyclic structure. In this case, you end up with a cyclohexene ring where the X group is coming off the side that is not part of a pi system. Importantly, the new bonds formed are located here, and the pi electrons now reside in the carbons that previously were just a sigma bond. So that is where this pi bond is located. When performing Diels-Alder reactions on dienophiles that are either cis or trans substituents, we need to consider the stereochemistry involved in the product formation. So again, we end up with the cyclohexene ring, and since the reactant dienophile was cis for the substituents coming off the alkene, they need to remain cis on the product. So in this case, we would draw both of them as wedges. Since we form new stereocenters, we need to indicate the stereochemistry, and we do so by drawing a wedge for both, indicating that both are going in the same direction. For the trans dienophile, where the substituents are going in opposite directions, this gives rise to a cyclohexene ring, where now we need to indicate that both of them are going in opposite directions. So we would draw one as a wedge and one as a dash to indicate that they are trans to one another, as opposed to if they are cis to one another. Importantly, Diels-Alders require that the diene be in the S-cis conformation in order to proceed. So for that reason, any time you have a cyclic system that locks the position into the S-cis conformation, indicating that around this sigma bond, the alkenes are cis to one another, this is actually going to speed up the reaction. Now, once we have our diene in the S-cis conformation, it can react with any dienophile that contains a pi bond, specifically ones that have electron withdrawing groups like esters, for example, or nitro groups or cyano groups. Anything that will activate the dienophile will make this reaction proceed more rapidly. And since there are 2 pi bonds present in this dienophile, this means that only one of them is being used in the Diels-Alder reaction. So only one set of those electrons are being used. So in our cyclohexene conformation, we need to indicate that fact that there's still going to remain a pi bond, as well as on the opposite side of the cyclohexene ring, so we end up with a system with 2 pi bonds. Now importantly, this also means since these carbons are sp2 hybridized, we do not need to indicate wedges or dashes indicate that they are stereocenters because they are sp2 hybridized and thus planar. For that reason, the esters that are present would actually just come off as straight lines. So we need to indicate that with a straight line since this is an sp2 hybridized carbon and they are trigonal planar and do not contain stereocenters. Now for this example, in addition to this ring conformation, this cyclopentadiene being locked into the S-cis conformation, we also need to consider the fact that our dienophile contains 2 pi bonds in these aldehydes. So remember, an aldehyde is CHO, but you can also draw it like this. Both of these are representing an aldehyde. And these pi electrons present in this electron withdrawing group are going to be stabilized in the endo position. So for that reason, now that we have this fused ring cyclic system, where we had our cyclopentadiene, which contained 5 carbons, we need to still contain those same 5 carbons. So those are positions 1, 2, 3, 4, and 5, whereas our new cyclohexene ring is a part of this boat conformation. And then we need to consider the endo rule for these pi containing electron withdrawing groups on the dienophile, so both of these substituents would be going in the downwards direction. And again, this is called the endo rule, where the substituents would be pointing towards the larger ring as opposed to the smaller fused ring up at the top. For the electrocyclic reactions, remember these pi electrons are allowed to move in such a way that you can actually close this ring and end up with a system where you have moved the pi electrons, and this is called an electrocyclic reaction. Remember that both of these reactions can either proceed either through heat or the presence of light. And it's important to remember that the conditions that are used determine the stereochemistry that results in this closed ring system, because the orbitals will either rotate disrotatory or conrotatory, depending on which conditions, heat or light, were used in the system. Importantly, the same is true for 4 pi systems as it is for 6 pi systems or even 8 pi systems. In the case of this 4 pi system, we were going to end up with a cyclobutene ring, and notice that the equilibrium favors the products in the 6 pi system, but the reactants in the 4 pi system. Largely, this comes from the ring strain that would result in this cyclobutene ring. For sigmatropic rearrangements, we have Claisen reactions and Cope rearrangements. And remember, sigmatropic just means that the sigma bond is changing locations. Importantly, for a sigmatropic rearrangement to occur, this is going to move the pi electrons and end up breaking this sigma bond and moving it here. So we are breaking this sigma bond and we are making a new one at this location. This is going to result in a new product in the presence of heat, where you end up moving that sigma bond in addition to moving the pi electrons. So now this would be the reaction that occurs to create this product. And again, remember, the location of our sigma bond is changing places, which is why we call it a sigmatropic rearrangement. Claisen rearrangements also undergo a very similar process, and notably, this is going to lead to the cause of a sigma bond being changed from locating between the oxygen and the carbon on this side to being present on the other side. So in the presence of heat, this is going to give us a new product where you have a carbon-oxygen double bond, as well as another pi bond on this side, and notice that our sigma bond has moved. Importantly, all of these rearrangements are 3-3 rearrangements because the carbons involved in this movement and where the breaking and the making of bonds occur, there are 3 atoms up top and 3 atoms below. So we often call those a 3-3 sigmatropic rearrangement. Now let's try some reactions at benzylic positions and reductions of benzene. Pause the video, try these problems independently, then resume the video to check your answers. While benzene itself is typically very unreactive, the benzylic carbon position, meaning the carbon position next to the benzene ring, typically is very reactive. For that reason, it can undergo things like oxidation using either of these conditions, which would completely oxidize off the rest of the remaining carbon chain, no matter what it is, as long as there is a carbon-hydrogen bond, into a carboxylic acid. So for this reason, this product leads to the formation of a carboxylic acid at that benzyl position. Additionally, since there is a carbon-hydrogen bond at that benzyl position here, we can do things like brominate using halogenation using a free radical. Specifically, NBS is what allows us to produce that bromine radical. Therefore, this product would be the bromination at that position through a mechanism that follows a radical formation. In addition, if there are already substituents at that benzylic position, like for example a benzylic bromide, we can do things like substitution reactions. In this case, it would be an SN1 reaction replacing the bromine with something like an alcohol And this would be an SN1 reaction because it is a quaternary carbon, and therefore it can't undergo a SN2 reaction where everything happens at the same time. However, in the next case, we can follow an SN2 reaction where everything happens at the same time and the water would attack nucleophilically in order to replace that benzyl bromide in order to give us a benzyl alcohol. We can also do things like elimination reactions. Specifically, using H2SO4, concentrated sulfuric acid, you can eliminate this alcohol in order to produce an alkene. So an alkene will now be present at that benzylic position. The same is true if you use a strong base like sodium methoxide in the presence of a benzyl bromide. So for example, this would produce the same product where you have one of the substituents as a methyl group and one as an alkene. Also, if you're getting value from this video, make sure to subscribe to my channel for more chemistry content. Now let's get back to talking about the reduction of benzene. Now typically benzene is going to be incredibly stable because it's an aromatic compound with a fully conjugated pi system with a cyclic structure that satisfies Huckel's rule of 4n plus 2 pi electrons. Now importantly though, under extremely forcing conditions in the presence of hydrogen gas, radii nickel at high temperatures and high pressures, you can actually do a full reduction of benzene. This would lead to the formation of cyclohexane, where all of the pi bonds are completely reduced and replaced with carbon-hydrogen bonds at every position in order to fully saturate this carbon. The same is true for benzene that contains positions that are either electron donating or electron withdrawing. Now importantly, when you have an electron donating group, this is going to lead to reduction at the other carbons. So what I mean by that is that you're going to end up with 2 pi bonds instead of 3, and importantly, the reduction is going to happen at the carbons that are not attached to that electron donating group. Now importantly, the opposite is true for when you have an electron withdrawing group. In this case, you would still end up with 2 pi electrons. However, the reduction would actually happen at this position that contains this electron withdrawing group, which we know since it has this carbonyl group. Therefore, notice this is the position that was reduced as well as this carbon. However, in the presence of an electron donating group, it's not the carbon attached to that substituent, but in fact the ones adjacent to that. So for that reason, this is going to be the reduction with an electron donating group, and this would be the reduction with an electron withdrawing group. Benzene can also undergo a variety of what are called electrophilic aromatic substitution reactions. When benzene is introduced to bromine gas in the presence of a Lewis acid of iron tribromide, this is going to do a bromination, an electrophilic aromatic substitution, at one of the positions to place a bromine on the benzene ring. Similarly, chlorination can happen in the presence of chlorine gas and a different Lewis acid in aluminum trichloride. So this would place a chlorine substituent on that benzene ring. Nitration occurs in the presence of nitric acid and sulfuric acid, where you can place a nitro group onto the benzene ring, which is important because this can undergo a variety of subsequent reactions like reduction to a primary amine or an aniline. Specifically, in the presence of a metal like either iron or zinc, in addition to hydrochloric acid, followed by step 2, which introduces a base, this produces a reduction of NO2 to NH2. So therefore, we are able to produce an primary amine in this way, creating the aniline benzene derivative. Adding fuming sulfuric acid by itself in the presence of benzene is actually going to place an SO3H group or a sulfonation at the position where now we can do what's called a sulfonation. Now importantly, this reaction is one of the only ones that are reversible, meaning you can go back to benzene just by adding a little bit more of dilute sulfuric acid. So dilute H2SO4 will allow you to go backwards to benzene, meaning that it's one of the functional groups that can be installed to benzene and subsequently removed. The next two reactions are Friedel-Crafts reactions, specifically acylation, and alkylation. So alkylation and acylation are always done in the presence of aluminum trichloride, where you can place either an acyl group, meaning a carbonyl compound can be added in order to place, for example, this group, or you can do an alkylation just to add a single alkyl chain to your benzene ring. Now importantly, in this case, we were using methyl chloride, but you need to consider the fact that in the case of Friedel-Crafts alkylations, if you're producing a primary carbocation through this process or this mechanism, then you can get a rearrangement in these reactions. For that reason, if you wanted to install a linear alkyl chain, one would likely use Friedel-Crafts acylation followed by reduction of the carbonyl group in order to produce a linear alkyl chain. So we can form a linear alkyl chain if we reduce this ketone into an alkyl group using, for example, zinc in the presence of mercury and HCl, this would allow us to do the reduction of a ketone into an alkyl chain. Now, importantly, if you do a Friedel-Crafts alkylation, you are creating a benzyl position or a benzyl carbon-hydrogen bond with which you can do all of those reactions that we just learned about. For example, radical bromination at the benzyl position or oxidation into carboxylic acids. Now let's look at ketones and aldehydes. Pause the video, try these problems independently, then resume the video to check your answers. Ketones are an incredibly versatile functional group that are capable of tremendous amounts of chemical reactions, specifically those listed on the screen. Specifically, we've talked about reactions where you can form hydrates by replacing two of the alcohols or the waters that are present in the addition of a carbonyl carbon, which is called nucleophilic addition reactions. Other types of nucleophilic addition reactions are things like forming acetals. So instead of having the hydrate formed, instead you would have two ethers formed, which would be called an acetal. In the presence of a molecule that contains two alcohols, which is called a diol, you can make cyclic acetals as well, which are an incredibly useful protecting group for things like ketones when undergoing multi-step synthesis. Additionally, in the presence of an acid and a primary amine, we can form things that are called amines. So this is going to be a carbon-nitrogen double bond, and it is going to contain a single R group coming off. And this is what happens when you use a primary amine. When using a secondary amine in the same reaction with a catalytic amount of acid, you form what are called enamines, where you have the nitrogen to carbon single bond. The nitrogen is now a tertiary nitrogen, and there is an alkene at this carbon position. Now, if you're using a catalytic amount of acid and hydrazine, which is NH2NH2, this is going to form what is called a hydrazone. So a nitrogen to nitrogen bond is formed as part of this imine structure, IMINE, and this can undergo subsequent reactions like the Wolff-Kishner reduction, where you can actually completely remove this to just create two brand new carbon-hydrogen atoms. And this is done in the presence of a strong base like sodium hydroxide, typically water, and also in the presence of heat. In addition to these nucleophiles adding at the carbonyl carbon position, we can consider several others, specifically nucleophilic carbons. So for example, a Grignard reagent creates what is effectively an R- group or a nucleophilic carbon, which will do a nucleophilic addition at that carbonyl carbon position. Following acidic workup will allow us to create a new carbon-carbon bond in addition to now creating that alcohol. Under basic conditions, cyano groups or nitriles will also add nucleophilically at that carbonyl carbon position, creating what are called cyanohydrins. So a cyanohydrin is a carbon that contains both an alcohol and a nitrile at the same carbon position. We've also learned about using Wittig reagents, which are going to be a carbon to phosphorus ylide. That means that you have a compound that is overall neutral, but the adjacent heteroatoms are oppositely charged. So remember, a resonance structure for this would make the carbon nucleophilic and negatively charged, whereas the phosphorus would be positively charged. This is going to allow us to create new alkene bonds or carbon-carbon double bonds, specifically replacing the oxygen in order to create a brand new alkene at this position. So this would be our product of our Wittig reaction. And again, that is Wittig, Wittig. The last one is using an anhydric acid in order to create an ester. So in this case, we would create a brand new ester compound, which is a carbonyl carbon where you have another carbon-oxygen bond in addition to some R group that was present here. Now let's talk about carboxylic acids. Pause the video, try these problems independently, then resume the video to check your answers. Largely, there are a few different ways to produce carboxylic acids. We've already seen the case where you have a benzylic carbon-hydrogen bond that can undergo oxidation with potassium permanganate in order to make a benzyl carboxylic acid. Additionally, we can make carboxylic acids by using alkyl bromides. Specifically, if we have an alkyl bromide that can undergo a substitution reaction with sodium cyanide, this will produce first a cyano group at the position where you had the bromine. So for example, this would produce an alkyl cyano group. From here, remember that cyano groups can undergo oxidation to produce carboxylic acids via the addition of an acid and heat. Therefore, the subsequent transformation for this would be a carboxylic acid, where now the carboxylic acid is formed at this position. Additionally, we can form carboxylic acids via a Grignard reagent. So the first step in this reaction would be to create your Grignard reagent, where the magnesium would insert into the alkyl bromide bond. Following the formation of the Grignard reagent would react with CO2 and after acidic workup would produce a carboxylic acid. So this was another method to form carboxylic acids of alkyl bromides. Finally, it's important to remember that carboxylic acids can subsequently be reduced via lithium aluminum hydride or some boron ester species. Each of these would produce primary alcohols where you are reducing the carbonyl oxygen, so therefore you're leaving behind two brand new CH bonds. Now let's talk about the preparation and reactions of acid chlorides. Pause the video, try these problems independently, then resume the video to check your answers. Acid chlorides are going to be the most reactive carboxylic acid derivative. In fact, they can be turned into all of the other carboxylic acid derivatives. So we just learned about how to turn a carboxylic acid into an acid chloride using thionyl chloride, and we can actually turn the acid chloride into a carboxylic acid simply by the addition of water. We can also turn acid chlorides into esters through the addition of an alcohol, so ROH, where the R is any alcohol, could be ethanol, methanol, etc., and pyridine. So pyridine is often the solvent used in this process, and we add an alcohol to create a brand new ester. We can turn acid chlorides into amides. So an amide is going to be your carbonyl that contains a nitrogen containing group on the other side of the carbon, just by adding excess amounts of an amine. So ammonia, for example, an excess amount meaning XS. Ammonia would allow us to create a primary amide, but we could also do something like create, by using excess secondary amines, to create a brand new tertiary amide. So this is a way that we could add different types of R groups to our amide. We can also use acid chlorides to create ketones. So remember, a ketone is going to be an R group coming off the carbonyl by using an organometallic reagent, which we'll learn about more in this course. So R2 copper lithium, that's called a Gilman reagent. Acid chlorides also undergo reactions with Grignard reagents. So RMgBr, for example, is what's called a Grignard reagent. And when you also have an acid in your system, so H3O plus just meant to depict any sort of acid, we can actually create a brand new alcohol species that contains two different R groups. So we can create brand new tetrahedral carbons with an alcohol on them by adding an excess amount of these Grignard reagents in the presence of acid. We can create primary alcohols by using lithium aluminum hydride, which will allow us to create a primary alcohol where the other R groups would just be hydrogen atoms. And then finally, we can also create aldehydes. So remember, an aldehyde is going to be that carbonyl with a hydrogen coming off the carbon by using this reagent. So lithium aluminum OR3 in the presence of an acid. Like acid chlorides, anhydrides can be converted back to carboxylic acids simply with the presence of H2O or water. Again, like acid chlorides, anhydrides can be converted into esters through the addition of an alcohol. So an ester can be created through the addition of an alcohol. Again, like acid chlorides, we can create primary amides simply by adding different amines to create brand new amide bonds. So a primary amine could be formed through the addition of excess ammonia, or if we wanted to make a secondary or tertiary amide, we would simply add different types of amines to our system. So excess amines can be used to create brand new amides from anhydrides. Again, like acid chlorides, we can actually create ketones by simply adding that Gilman reagent, which again was R2 copper lithium, can be added to anhydrides to make ketones. Alcohols can be made by adding excess amounts of Grignard reagents. So again, that's some R group with magnesium bromide, for example, and some acid, H3O plus, we can create brand new alcohols as well. And we can create ones that have a stereocenter potentially because we're creating tetrahedral alcohols. Just like acid chlorides, we can also make primary alcohols by using something like excess lithium aluminum hydride as well as water or acid to create that primary alcohol. So remember, a primary alcohol is going to be attached to a carbon with two other hydrogen atoms attached to it. And again, like acid chlorides, we can use lithium aluminum ethers in order to create brand new aldehydes. So this allows us to create aldehydes, which again is carbon to hydrogen with the carbonyl functional group. One of the simplest ways to make esters is going to be through deprotonation of a carboxylic acid, followed by an SN2 or substitution reaction to create a brand new ester bond. A more common way that people make esters, though, is called Fischer esterification, where you use an alcohol and some catalytic acid, and you can convert carboxylic acids very readily into brand new esters. And again, this is called Fischer esterification. So Fischer esterification is the most common way that these types of esters are made in industry. The mechanism for Fischer esterification follows a pathway that you might predict, where the catalytic amount of acid is allowed to protonate that carbonyl oxygen to create a brand new positively charged species, which will allow for this carbonyl carbon to be attacked by things like our alcohol. So once we have made this more electrophilic, the lone pair on an oxygen from alcohol will come up, kick up those electrons to allow us to create a brand new tetrahedral alcohol and allow us to further undergo the transformation to an ester through a series of proton transfers. So remember, we still have plenty of our alcohol present, which has lone pairs on the oxygen, which will deprotonate that OH group, allowing us to create a neutral species. So now we have a fully neutral compound where we have two alcohols and an OR group. From here, one of the alcohols can be protonated by the brand new acid that has been formed, allowing us to create a good leaving group, which is going to be an OH2 derivative. So we have our alcohol, we also have a brand new OH2 that is positively charged, and our OR group. From here, the electrons can come down from one of the oxygen atoms and kick off that good leaving group, allowing us to create a brand new protonated ester, where now this proton that is on the carbonyl oxygen can subsequently be deprotonated by, for example, the alcohol that is still present in our compound, allowing us to finally generate our brand new ester. Nitriles are commonly made through substitution reactions with alkyl halides. For example, an alkyl bromide will undergo a substitution reaction with sodium cyanide to create our brand new nitrile. Additionally, nitriles can be made from amide bonds. So remember, an amide is going to be a carbonyl compound that contains a nitrogen-containing group on the carbonyl carbon by adding, again, that thionyl chloride that we've learned about in the preparation of acid chlorides in order to create our brand new nitrile. And the byproducts of this are going to be that sodium dioxide and hydrochloric acid. Now, nitriles and amides are unique in that they really only undergo two different types of reactions. So they are the least reactive of the carboxylic acid derivatives, and therefore they typically only create one other type of functional group transformation, and that is going to be the creation of a primary amine. So a primary amine can be created from both of these. From nitriles, we just add lithium aluminum hydride in the presence of water to create our primary amine. And we use the exact same reagent, and actually the lithium aluminum hydride can reduce this carbonyl oxygen to again create that primary amine. Now let's talk about enol and enolate reactions. Pause the video, try these problems independently, then resume the video to check your answers. Via a process that proceeds through enols and enolates, we are able to do alpha halogenation, or different types of reactions at alpha carbons of carbonyl compounds. Remember, the alpha carbon is going to be near the carbonyl carbon, which is electrophilic, and the alpha carbon is going to be the carbon that is directly adjacent to that. So in this ketone example, there are two alpha carbons, which contain very acidic carbon to hydrogen atoms. Of both ketones and carboxylic acids, we can do an alpha halogenation, meaning that at the alpha position, we can place a halogen, in this case bromine, under acidic conditions, we can add a bromine atom to that alpha carbon. Importantly, for carboxylic acids, there's only a single alpha carbon, since the other side contains the hydroxyl portion of a carboxylic acid, meaning that the carboxylic acid would be halogenated at that alpha position only, so we would place a bromine at this position. The haloform reaction is actually a two-step reaction in which you can take a ketone and turn one of the R groups into a carboxylic acid. So this is going to place a hydroxyl group here via a two-step process where first you brominate and then subsequently replace that bromine with the hydroxyl group to make this carboxylic acid. Additionally, enols and enolates allow us to create brand new carbon-carbon bonds through what is called the aldol reaction, like aldol addition or aldol condensations. In this first example, an aldol addition is going to allow us to create a beta hydroxy ketone where we can create a brand new carbon-carbon bond that adjoins these two species. We call a beta hydroxyaldehyde because at the beta position is where the hydroxy group is. Again, this is called an aldol addition. Importantly though, through the addition of a tremendous amount of heat, we could actually do what is called an aldol condensation, where the entire hydroxy group is actually removed and what you are left with is an alpha beta unsaturated aldehyde. So now you have the alpha beta because at the alpha and beta positions is where you can find this unsaturated alkene. We can also do crossed aldol additions where you have two different types of carbonyl compounds that react to form a new carbon-carbon bond between the two. That's called a crossed aldol reaction. And in the presence of a strong base and heat, we can do this crossed aldol addition, allowing us to generate that alpha beta unsaturated aldehyde. So in this case, we would create this alpha beta unsaturated aldehyde. And again, the name unsaturated comes from the fact that there is an alkene present in here. And again, this is at the alpha and beta positions. Additionally, it's possible to do a cyclization aldol reaction in where you deprotonate the alpha hydrogen at one of these positions and it can react at a different carbonyl functional group on the same molecule. This is called an intramolecular aldol condensation. And the product of this reaction is going to contain the same number of carbon atoms, in which case this is going to be 6. But importantly, the reaction happens at the alpha position, which would be here, and to the 5 position, so our ring would actually be a 5-membered ring with a methyl group coming off of it. So this final product should look like a 5-membered ring, still remaining our ketone, and it's going to be unsaturated, and at that unsaturated position is where that methyl group is coming off. For esters, we can also do what are called Claisen condensations. In a Claisen condensation, we are again forming that enolate between the alpha carbon and the carbonyl group of an ester. Using the deprotonation of a strong base like sodium ethoxide or LDA, we can do this Claisen condensation in order to produce a brand new carbon-carbon bond where you will be left with a product where you have formed this new carbon-carbon bond at this position. You can also do a crossed Claisen condensation between two different esters as long as one of them does not contain a free alpha carbon that contains a hydrogen bonding that would be deprotonated in order to get a single type of product. For example, this one is the only one that contains an acidic alpha carbon hydrogen, which would be deprotonated by the strong base like sodium ethoxide or LDA, generating a carbon-carbon bond from this position to here, so that is going to allow us to make our product, which again is going to contain that brand new carbon-carbon bond, and you would lose the ethoxide portion, thus allowing us to generate this product where you are left with this ester on this side. And then just like for aldol reactions, we can also do an intramolecular, meaning on the same molecule, condensation, which would allow you to produce this new 5-membered ring where the ketone is here, and the new carbon-carbon bond is formed at this position, leaving behind our ester. Now let's talk about enol and enolate reactions. Pause the video, try these problems independently, then resume the video to check your answers. Via enolate ions, we can also alkylate at the alpha carbon position of different types of molecules. Importantly, depending on which base you use, like sodium hydride or LDA, you will get a different isomer or a different constitutional isomer that is formed at the alkylated position of each alpha hydrogen. Via enolate ions, you can also alkylate alpha carbons depending on which base you use at different locations. So for example, for sodium hydride, since it is a smaller base, it would deprotonate the alpha carbon at this position, the more substituted, or LDA would instead deprotonate the alpha carbon hydrogen that is at the less substituted position, allowing us to create an enolate that will allow us to form two different types of alkylated positions. The R group will undergo a substitution reaction at those deprotonated positions, so as I mentioned for the sodium hydride example, the alkylation would take place at the more substituted position. Whereas for LDA, the less substituted position would be the one that gets alkylated, so for that reason, that product would be alkylated here. Importantly, you can also do Michael additions once you have formed enols or enolates through stabilized carbon nucleophiles like Gilman reagents or other Michael acceptors. So in this first example, we would alkylate at this position because the Gilman reagent is less hard or is a softer Lewis acid, allowing us to alkylate at this position. So the product that would be formed is going to be alkylated at that position, allowing us to generate a product that has a new R group at this position. Additionally, we can do reactions where we would deprotonate this alpha hydrogen, which is going to be incredibly acidic due to its position between these two carbonyl groups, allowing us to alkylate with this Michael acceptor again at this position, which is going to allow us to make a product that looks like this, and where we still have these two carbonyl groups and the alkylated position is here, so this is going to be our final product. Now let's talk about the preparation of amines. Pause the video, try these problems independently, then resume the video to check your answers. For synthesizing amines, I've grouped these three reactions below because they follow a similar pathway. First, transform a functional group into something else, and then subsequently reduce that functional group, which likely contains the nitrogen in it, into a primary amine. For example, the first step is going to extend our carbon chain by adding a CN group to the position where the bromine used to be, doing a substitution reaction, specifically an SN2 reaction. Now from here, lithium aluminum hydride followed by the addition of water allows us to reduce that position and extend our carbon chain to make this primary amine. Notice that this product contains one additional carbon to our starting material, which is what sodium cyanide does by extending the carbon chain. Conversely, using sodium azide, you would still do a substitution reaction. However, importantly, the carbon chain is not extended because this azide molecule will do a substitution and not extend the carbon chain. However, once you have produced this azide complex, this alkyl azide, you can do reduction using either hydrogen over platinum or again that lithium aluminum hydride followed by the addition of water in order to reduce this to the primary amine, which is going to now be NH2. The next example uses carboxylic acids to first convert to acid chlorides using thionyl chloride and then subsequently create the amide bond using an excess amount of the amine. So our product here is going to be an amide. Once we've produced this amide, we can reduce the carbonyl functional group using, again, lithium aluminum hydride followed by the addition of water to create our primary amine. Now, importantly, all of these different methods allow us to produce primary amines. Additionally, we know of the Gabriel synthesis and reductive amination, which allow us to synthesize amines. Specifically, using this phthalimide molecule, we can make amines first by deprotonating the hydrogen attached to the nitrogen, making a very nucleophilic nitrogen, which would undergo a substitution reaction of alkyl bromides, and then using hydrazine to liberate the phthalimide molecule, allowing us to leave behind the primary amine, which in this case is going to contain a product which looks like this. For reductive amination, we are always doing a process that proceeds through an imine. So first we protonate the carbonyl oxygen, then the amine will attack the carbonyl carbon position, and then subsequently sodium cyanoborohydride will do a reduction of an imine in order to make an amine. Using ammonia, this is how we make primary amines. So in this case, this would be our product. Using a primary amine as our starting material, we would make a secondary amine where you have a nitrogen attached to two R groups. And starting with a secondary amine, we can make a tertiary amine. So in this case, there are going to be three R groups coming off of that nitrogen, making it a tertiary amine. Now let's talk about the reactions of aryl diazonium salts. Pause the video, try these problems independently, then resume the video to check your answers. One of the most popular reactions for this are called Sandmeyer reactions, where you take copper salts, like for example copper chloride, and you can exchange the substituent to a chloride from the diazonium salt. Similarly, we can do this for copper iodide and copper bromide to generate the new aryl halide species in exchange for the diazonium salt. The Sandmeyer reaction also works for cyanide, so you can use copper cyanide to exchange this position for a new cyano group. And importantly, remember that we have already learned about reactions where you can transform cyano groups into, for example, carboxylic acids through oxidation. So this is a powerful way to install brand new functional groups along an aryl compound. There are other examples as well that are incredibly powerful. One of those such examples are fluorination, where you can actually exchange the diazonium salt for a fluoride. Another example that I want you to consider that may seem relatively simple or straightforward is going to be reduction. Through adding something like phosphoric acid, we can actually exchange that diazonium salt for just a simple hydrogen. And I want you to keep that one in mind because we can actually use diazonium salts to direct functional groups and direct synthesis and then subsequently reduce the diazonium salt to get rid of it. So it may be a powerful way for you to utilize this tool in organic synthesis. And then the final example that I want you to consider is the fact that we can exchange this diazonium salt for an alcohol. And we do this by using the conditions of using sulfuric acid, H2SO4, in water with a little bit of heat, which I'll indicate with the delta symbol. Now let's talk about some reactions involving organometallic compounds. Pause the video, try these problems independently, then resume the video to check your answers. Harnessing the power of organometallic chemistry allows us to do incredible transformations like form new carbon-carbon bonds. Importantly, the first step then is going to be to create your organometallic reagents, which are anything that has a metal attached to a carbon. The way that we make lithium reagents is by taking an alkyl halide, adding 2 equivalents of lithium, and forming our new organolithium species. Similarly, we form Grignard reagents by starting with an alkyl halide, adding magnesium turnings in ether, and forming our Grignard reagent, which inserts itself into the alkyl halide position, allowing us to create our Grignard reagent. We can also create what are Gilman reagents through a 2-step process which begins by making an organolithium species, same as in the previous reaction, however following that up with a copper salt, allowing us to create a brand new Gilman reagent which contains a copper and lithium in it. We also learned about Suzuki couplings, which allow us to take any vinyl or aryl boronate ester species and couple it with an alkyl or aryl halide to create a brand new carbon-carbon bond by attaching the new species at this position where you would split the alkyl halide and the organoboronate ester species. Forming the new carbon-carbon bond at that location, this allows us to make brand new carbon-carbon bonds, which contain a brand new carbon-carbon bond formed at that position. And again, this is called Suzuki coupling. And that covers all the reactions of organic chemistry too. If you want to dive deeper into any of these reactions, I would encourage you to check out this playlist for more in-depth videos. If you found this content useful, I would encourage you to subscribe to my channel to check out more chemistry content. I'll see you in the next video.